In today's tutorial, you will learn how to simplify a numeric radical. If you're following along in your notes, write this in the table of contents with the appropriate page number. All right, let's get started. The learning target for today is that you can simplify radical expressions. For this lesson, the radical expressions will have only numbers, no variables. In order to do that, your success criteria are that you have to be able to recognize a perfect square number, you have to be able to find square roots, and you have to be able to rewrite your radical expression in simplest form. So let's begin by learning the names of the parts. Any number outside of the radical sign is called a coefficient, and it's technically multiplying whatever is underneath that radical sign. The radical sign, which is this shape here, is often called a square root sign. And the reason it's called a square root sign is because if the index number is a 2, then you have a square root. But since 2 is the smallest index number you can have, we often leave it invisible. So if you have a different index number here, say a 3, you can't call it a square root sign anymore. So its official name is a radical sign. If there is no number, you can call it a square root sign. But as soon as you place a different number in the index position, it gets a different name. That's a 4th root, or a 14th root, or a 214th root. So technically the name of that symbol is the radical sign. And the number, the teeny tiny number, here is the index. But the larger number is a coefficient. So let's take a look at an example of a radical expression. Right here we have the number 2, and it's multiplying the square root of 10. So we pronounce this 2 square roots of 10. 2 times the square root of 10. Now, we often leave expressions in this form instead of multiplying 2 times the square root of 10, which would give us a decimal number that goes on forever and ever and ever and is irrational. So if a problem ever asks you to find an exact solution, and there are roots involved, then you need to leave it in simplest form and not convert it to a decimal, because that's not an exact answer. This one here is pronounced 6 cube roots of 5. So that's 6 times the cube root of 5. All right. Let's talk about what you can do with radical numbers. So there's 4 operations, and you can do all 4 operations with radical numbers. But certain operations, like addition and subtraction, are limited to how the number can look. Like, let's say you're adding fractions, right? You are limited to adding fractions that have like denominators. And the same is true with radicals. So when we continue in a future lesson and we perform operations, it's important for you to understand whether or not you are like terms. So if you're a radical expression, like terms have like radicands. Remember, the radicand is the number below the radical sign. So these two are like terms. It does not matter what your coefficients are. What matters is the radicand. If the radicand matches, then you have like terms. If the radicands do not match, like this example here, then these are not like terms. You cannot add them together, you cannot subtract them. You can multiply them, you can divide them, but you can't add or subtract them, because when adding or subtracting, you have to have like terms. All right, let's take a look at a few. Can I add these two together? Well, you have to always ask yourself, do the radicands match? And if they do, then yes, you can. Notice what happens when I add them together. The coefficient of 4 is added to the coefficient of 7, giving me a new coefficient of 11. But the radicand remains the same, kind of like adding fractions. The radicand stays the same when you're adding. All right, how about this one? 4 square roots of 3 plus 4 square roots of 5? Well, just because the coefficients match doesn't mean you can add. If the radicands don't match, you can't add them. So it's not that this problem has no answer, it's just that the answer is 4 square roots of 3 plus 4 square roots of 5. And if you can't do the math, you leave the math. Alright, I think you're ready to practice a few with me. Watch this, and then you'll try some on your own. 8 square roots of 3 plus 3 square roots of 3. Add the coefficients only. 11 square roots of 3. Remember, the radicand stays the same. Now this one is a subtraction problem. 4 square roots of 7 minus 6 square roots of 7. That gives us negative 2 square roots of 7. How about letter C? What do you guys think about this one? 5 square roots of 10 plus another square root of 10. Well, you can't see it, but there's an invisible 1 coefficient there. So the answer is 6 square roots of 10. How about the last one? 4 square roots of 5 minus 2 square roots of 3. If you said you can't add them or subtract them, you're right. You can't. They don't have like radicands. Alright, I think you're getting the hang of it. Try these 4 on your own. Please pause the video now. Okay, let's take a look and see how you did. Here are the answers to these 4 questions. Notice on question number 2 that you do not have like radicands. And remember, when adding or subtracting, the radicand always stays the same. Only the coefficient can change. Now, for question number 4, oftentimes I'll have a student ask me, is it okay if I put a 1 here? And the answer is technically, you are not wrong, but you are long. Nobody asks you how old you are and you say, oh, I'm 13 over 1, right? Even though there's technically a 1 underneath you. So I would say, leave that 1 off. Alright, now let's move into another type of question. Can you add these 2 together? You probably said no, but the answer is, actually you can. You just don't know how yet. These 2 radicals are not matching right now, right? The radicand of 3 does not match the radicand of 12, but the radicand of 12 can technically be simplified. And if I can write it in such a way that it comes out with a radical 3 in it, then I could add these together. Now, we're not going to practice adding these today. We'll do that in a future lesson. But the whole point of our lesson today is for you to recognize if this problem can actually be done or not. So let's get started with the actual simplifying. If I want to simplify the square root of 12, then what I want to do is I want to rename 12 as another number. And I'm going to write it as a product of 2. And hopefully, one of your factors is a perfect square. Okay, so it would be helpful if you memorize these first 15 perfect squares. And if you don't have them memorized, you could always write them down. They're just 1 times 1, 2 times 2, 3 times 3, 4 times 4, etc. Or you could take a quick pick. So let's get started. The square root of 12 can be factored. And I have 2 examples for you here. 4 times 3 and 2 times 6. But only one of these factorizations actually has a perfect square number. And that's the one on the left. 4 times 3 has one of its factors as something that I can take the square root of. That means it's a perfect square. But the others are not. I cannot evenly find the square root of 3 as a rational number, or the square root of 2, or the square root of 6. So even though these are both factored, this is the right way. When I factor the square root of 12 into 4 times 3, I can actually rewrite it as a product of those 2 factors. So that's the square root of 4 times the square root of 3. Now we won't be doing the multiplying today because what we want to do is write it as small as possible. And these 2 factors, square root of 4 and the square root of 3, have one that is square rootable. It's a perfect square. So what we're going to do is take the square root of 4 and leave the square root of 3. So our answer to the square root of 12 is that it's equal to 2 square roots of 3. And if I'm not sure if I'm right, I can simply turn my calculator on, perform the square root of 12, perform 2 square roots of 3, and see if my answers match. And they do. So I know I got it right. This is your check step. Alright, let's try another one. How about the square root of 40? Can you factor this into perfect square factors? So remember, you should be kind of going down your list, right? Your list of 15 perfect squares. So we're looking for factors of 40. So all of these are larger than 40. So those wouldn't even be worth checking. So I'm going to divide 40 by 36, divide it by 25, divide it by 16, divide it by 9, divide it by 4, and see if I get a whole number as an answer. So remember, you're looking for perfect square factors, not these. They're factors of 40, but I can't square root either one of them. So let's work with 4 times 10. So I can rewrite this as the product of the square root of 4 times the square root of 10. The square root of 4 is 2. Notice, once I take the square root, it comes out of the radical sign. So 2 square roots of 10. Get your calculator out and be sure to check your math. Alright, let's try another one. How about the square root of 50? Now, I know that's 5 times 10, but remember, you're looking for perfect square factors, not just any factors. So let's start thinking about our perfect squares. 1, 4, 9, 16, 25. Ah, we found it. 25 times 2 is a perfect square factor. So I can rewrite that as the square root of 25 times the square root of 2, and the square root of 25 is 5. So 5 square roots of 2 is the solution to being simplified, right? Alright, let's try another one. How about the square root of 48? Again, you're looking for perfect square factors, so get your calculator out and start guessing. You can do that. So you can start with a lower number, but it's best to start with the highest number possible. So I would have tried anything lower than 49, 36, 25, 16, 9, etc. So the square root of 16 times the square root of 3 is the same as the square root of 48. You take the square root of 16 and you get your final answer. This is in simplest form. Now, sometimes you get a really big number and you start to get stuck. Get your calculator out and start with a perfect square factor in any order, but you might as well start with the larger ones, but let's just say you're not really thinking and just pick a random perfect square, like 16. Well, 294 divided by 16 is not a whole number, so it's not a perfect square factor, right? It's not a factor. How about dividing by 4? Nope, that doesn't result in a whole number either. So I try another perfect square number. Maybe, well, I know 25 is not going to go into it, right? Because 25, 57, I definitely know that's not going to work. So I'm going to skip up to 36. And that's not a whole number either. So I go to the next perfect square after 36, which is 49. And that results in a whole number. So this isn't the answer, but I know that 49 times 6 are a good pair of factors. So 49 times 6 are my factors, right? The square root of 49 times the square root of 6 is another way of writing the square root of 294. This one is square rootable, this one is not. So my answer is 7 square roots of 6. Alright, hopefully you're getting the hang of it. If not, rewind the video before you start these next problems on your own. If you think you're ready, then pause the video now and give these 3 a try. Good luck! Okay, let's see how you did. 3 square roots of 6, 4 square roots of 5, and 6 square roots of 5. So that's how you simplify radical expressions. Now let's talk about what happens sometimes when you kind of go off on the wrong path. It doesn't necessarily mean you're going the wrong way, but maybe you're just not taking the shortest route. Like, what if you forget to find perfect square factors, and you just start kind of factoring using any numbers you want. Or you're not really paying attention, and maybe you do something called prime factorization, where you just keep factoring until you get to the very smallest number that you can. Right? When you get to the end of your tree, those are your total factors, whether they all line up or whether on all different levels. If you're the bottom of the branch, you're a factor. So 2 times 2 times 2 times 5. It looks different than the one on the left, but they're the same numbers. 2 times 2 times 2 times 5. So you could rewrite the square root of 40 like this. Not very helpful, and it's really long. The square root of 2 is not rational, the square root of 2 is not rational, the square root of 2 is not rational, the square root of 5 is not rational, right? I can't take the square root of any of these numbers. So what you can do is, instead of looking for perfect squares, is sometimes you can just look for something called pairs. So if you find a pair of numbers, they can come out and be a coefficient. But if what's left over is not a pair, then the product remains behind. All right, so if you forget, and you kind of find yourself in a little pickle and you're like, oh no, I factored it and none of these are square rootable, well, look for pairs. Remember, the pairs come out as themselves, not as a square root. Let's take a look at another example. Maybe you're finding the square root of 200 and you choose 4 as your perfect square factor. Well, that's good, but 50 is quite large. And if you wrote your answer as 2 square roots of 50, you wouldn't be done. And you might think you're done because you found your perfect square factor, but technically you didn't find the greatest perfect square factor. So sometimes when you find a perfect square factor, but your second factor seems kind of large, you might want to try factoring that number. Maybe you can find a perfect square, or maybe you're not really paying attention and you find two numbers that are not square rootable. Well, don't forget, you can keep going and look for pairs. So this can come out as a coefficient because it's a pair. This can come out as a square root. Square root of 4 is 2. And if more than one number comes out, you have to multiply them together. Now remember, this guy's still left over, so he stays under the radical sign. So the square root of 4 came out, and the pairs of 5s came out. And 2 times 5 is 10. So the square root of 200 is 10 square roots of 2. Now that's a long way of going about it. What if you had realized that the largest perfect square that goes into 200 is actually 100? The square root of 100 is 10. The square root of 2 cannot be done. All right, I think you've got the hang of it. Finish this exit ticket, choose the right answer, all right, hopefully you got it right. And that concludes our lesson on simplifying radicals.